So now let's do a sample problem. This one is going to be a little bit more difficult. I'm going to walk you through what we're doing. Okay. Calculate the amount of energy needed to convert 252 grams of solid ice at 0 degrees to hot water at 80 degrees. Okay, so what we're doing, if we go back to that heating curve that I showed you, right, where it was temperature, so big T versus time, little t, we're starting at ice, right, at 0 degrees, okay, and we're going to have to let it phase transition for a little bit, okay? So that means the temperature is not going to change, and then we're going to heat it up to liquid water at 80 degrees C. And so schematically what's going on here, during this leg of the calculation, we're going to have the delta H of fusion, all right? And during this leg of the calculation, we're going to be using the heat capacity. So it's going to be a two-part calculation, part 1 and part 2. Part 1 is just how much heat do we need to make it melt, and then part 2, how much heat do we need to make it rise in temperature. Okay, so part 1, to melt ice. What we need to do, I'm going to write that as Q1. Okay, so I don't have a formula for this because it's our stoichiometry, but I'll write a formula. It's going to be N times the delta H of fusion. Okay? And so what that means is I need to convert this 242 grams into moles. Okay? So let's see here. So that means my N is going to be 252 grams of H2O, and I know there's 18.01 grams of H2O in 1 mole. Okay, and so let's see here. So I get 252 divided by 18.01. And with 3 significant digits, I'm going to call it 14.0 moles. Okay, great. So now my Q1 is going to be 14.0 moles times my delta H of fusion. The molar enthalpy of fusion of ice is 6.01 kilojoule per mole. Okay, great. And let's see, I'm going to make that into joules as well. So 6.01. And the reason I'm going to make it joules is because I have my molar heat capacity in joules. So I could do either way. I could make this one kilojoules and keep this one in kilojoules because I want to compare apples to apples. Okay. Oh, and so actually I wrote CS on this little diagram, but because we just converted to moles, we're going to use CP. Okay. So I know 1 kilojoule is 1,000 joules. So that means 1, 2, 3. So that quantity is 6010 joules per mole. Okay, and the mole cancel. And so now I'm going to leave this number in the calculator and then just say times 6010, and that equals 84.1. It looks like. Yes. 1, 2, 3. So we'll keep it in joules again. 1, 2, 3, 4. Sorry. 8.41 times 10 to the 4th joules. So that's how much energy it takes just to melt the ice. We haven't even raised its temperature yet. We're just melting the ice. Okay? So now we've got water, and we've got water at 0 degrees. So now to raise the temperature, we're going to use now the N times CP times delta T. Okay? And so this is the equation that gives us this change in temperature, right? So we note that we have 14.0 moles for N. We note that the heat capacity, CP, is, there it is, 75.3 joule per mole per degree C. And now what about the delta T? Okay, so it's solid ice at 0 degrees initially, and it's going to end up at 80 degrees for the final temperature. So I can now say 80.0 degrees minus 0.0 degrees C. I could have just put 80 in there, but I did it just to be complete for this problem so you can see how it's going to work. Okay, and so now that's going to be 14.0 times 75.3 times 80 minus 0, which is 80. Okay. So now for this one, I get 8.4, 1, 2, 3, 4, 8.43 times 10 to the 4th joules. So this is amazing. Look, both of those numbers came out very similar. And so let's just think about what that means for a second, okay? It takes just as much energy to melt the ice as it does to then heat it up as water by 80 degrees. So now that means my total heat is going to be this Q1 plus Q2. Okay, so let's say that number plus 84100 equals, and I get that to be Q1 plus Q2, 1, 2, 3, 4, 5, 1.68 times 10 to the 5th joules. And I'm going to convert that to kilojoules just because that's such a big number. So in 1,000 joules, there's 1 kilojoule. So divided by 1,000, that's 168 kilojoules of total energy, right? So if I say divided by 1,000, so 168.4, 168 with 3 significant digits, okay? So again, when we're calculating these change in temperatures, when we're doing these calorimetry equations, keep in mind, right, that when we encounter a phase transition, okay, it's got to be the number of moles times the delta H. But then when we're on this rise, when the temperature is actually changing, that's where we use one of the two heat capacity equations, depending on if we have moles or if we have mass. Okay, so keep track of those.